Hello, this is my implementation of the paper BiScope. In this video, I will go over the problem being solved and past efforts to do so. I will give some background on BiScope and why I chose this paper. Then, I will go over the details of my implementation. And finally, I will go over my results from the paper. The high-level problem. AI-generated content is becoming increasingly common with tools like ChatGPT, but this means that AI-generated content is being passed off as being written by humans. A way to stop this, or curb this, is with AI detectors, which work by measuring how predictable text is. They do so by using features like perplexity and burstiness, which tend to measure like randomness in text. Some popular examples of this are GPT-0 and Quillbot. However, current detectors are flawed, and they can present false positives and cannot keep up with how fast LLMs are advancing. Because of this, AI detectors cannot be used reliably, and institutions need other ways to identify AI-generated text. This is where BiScope comes in. It was part of a paper submitted to the prestigious Near-IPS conference in 2024 by Hanshi Guo, Xiyuan Cheng, Xiaolong Jin, Zhou Zheng, Kaiyuan Zhang, Guanran Tao, Guanyu Shen, and Xiangzhu Zhang, and it uses a bidirectional cross-entropy loss calculation to evaluate AI-generated text. This means that it performs calculations by including both the preceding and the succeeding token information, making it far more reliable for text prediction. This is similar to a bidirectional RNN, like like was discussed in class. The paper also provides new datasets with challenging samples from 5 different text domains: ArcSIF summaries, code, creative writing, essays, and Yelp reviews. Another unique thing is that they utilize text summaries for training. So why did I pick BiScope? BiScope outperforms many state-of-the-art AI detectors in overall accuracy, and it is also insanely fast, parsing each sample in about 200 milliseconds, while other detectors average about 27 can go up to 27 seconds per sample. It also comes with several pre-existing datasets which are robust and make it easy to test and evaluate detection performance consistently. For my implementation, my goal is to analyze how AI detectors perform across different fields and identify the key factors that influence their accuracy. For example, comparing AI detectors on short form versus long form content and informal versus formal content. I also want to evaluate how older detectors hold up when tested on newer LLMs, in this case ChatGPT 5.1 and Claude 4.5 Sonnet. As for my implementation's details, the codebase was cloned from the original paper's GitHub repository. Since this detector is already top of the line, I could not find much to change in the actual methodology and chose to extend the experiments conducted in the paper instead. To do so, I formulated 12 brand new datasets with AI samples sourced from the latest LLMs, aka ChatGPT 5.1 and Claude 4.5 Sonnet. I took human samples from Kaggle datasets containing real text from news articles, Amazon reviews, IMDb movie overviews, and YouTube comments. I also made a program to refresh these human samples by randomly sampling them from these datasets to switch up training data. As for how to use the code, these are the commands given below. The detection algorithm is run using a Python command where each of the arguments are a JSON file. And the human samples can be refreshed using the shuffle.py program. My results are present in the paper, but as for its interpretation, we can see that ChatGPT is far easier to detect than Claude, which implies that Claude has become more human-like than previous versions. Across all domains, ChatGPT scored a much higher F1 score, which is our accuracy score in this case, compared to Claude. Higher F1 scores occurred when we were dealing with human samples which had high variation, such as YouTube comments and Amazon reviews. And we also saw lower F1 scores when dealing with human samples which have a set structure, for example, IMDb movie overviews, which resulted in the lowest F1 score. It works well on YouTube comments, but this may be due to the lack of specificity from LLM samples. LLM samples usually provide comments that can apply to a wide variety of YouTube videos, while YouTube comments taken from directly from the site are specific to that video itself. And we can also see that BiScope keeps good performance even with newer models. In conclusion, this work provides insight into how both AI generation and detection work. It also shows that LLMs are becoming increasingly human-like in their writing. Therefore, continuous experimentation and research are essential for detection models to keep up with LLM development. To finish off, I will execute the script present here. We are testing out the news dataset from Claude. Our program has finished executing, and as you can see, the F1 scores are present here. It's a five-fold F1 score, and this is the average F1 score. Uh, and if you compare the average F1 score here to the results present in the paper, it should be consistent with those results as well. And the features are also present in the results folder under the non-paraphrased Claude 4.5 Sonnet. Here we can see the scores and the features themselves. And that about wraps up this video report.